But yes, what I would like to talk about is some recent work on a one-way quantum repeater protocol based on near-deterministic photon-emitter interfaces, and it very naturally follows the previous talk actually, since it's the same type of repeater here, just a slightly, or actually quite different encoding. So probably you are already been given kind of the why do we care about quantum communication? You know, one of the key applications, at least, is this long distance QKD. And I'm sure you've been told one of the main challenges is that basically we have loss when we try to transmit photons in optical fibers that scales quite unfavorably with the distance. And therefore, there's been these quantum repeaters proposed to solve that question, solve that problem. And I will divide it into two classes. So basically, we have the two-way repeaters and the one-way repeaters. And if we start with the one-way, so this is also what you heard in the previous talk. So this is where we basically, in order to beat transmission loss, we take our qubit information and we encode it into an error-correcting code. One that specifically is very good at correcting for loss, but it should also ideally also correct other types of errors, other types of noise. Such that we have reliable transmission of the qubit from one repeater station to the next. And then that just basically continues all the way down the chain till we get to the end station. And kind of one of the main challenges also about these one repeaters is that generally they require quite good quantum operations because they're relying on an error correcting code. So usually if you talk about some generic error probability per qubit, then for most schemes, this should be around 0.1 per mil or something like that for the repeater to work over a long distance, that is. A good thing is that for these repeaters, the repetition rate is basically set by just the local processing rate, because you take a qubit, you encode it, and you send it off, and then you can start encoding a new qubit and send that off. And this is, I should say, stress that here I'm thinking about QKD, where you basically just prepare a qubit, send it down the line, and then measure it when you get it there. The repeater spacings for such repeaters here is quite small. So usually it's around 1 to 3 kilometers. And that's kind of in contrast to the more standard two-way repeater, where you take the total distance and you divide it into small segments, over which you can create entanglement by some heralded scheme. For example, these Baron-Cox schemes or other types where you take photons and you emit those from your quantum memories. You have some spin photon entanglement. And then by using a beam splitter, you can basically do a Bell measurement of the photons, thereby establishing entanglement between your memories. And this you can do in parallel for the different segments. And once two neighboring segments have succeeded, you can do another Bell measurements on the memories to swap entanglement to a larger distance. So what the two-way repeaters requires is that you actually have these quantum memories and that they are pretty long-lived compared to the one-way repeater, because you don't need to just keep your state there while creating your error correcting code, as in the one-way repeater. Here you need to keep it there while you wait for a heralding signal telling you whether it was a success to establish this entanglement over the link or not. And also you need to wait till the other link, the neighboring link, also has success before you can swap. That also means that the repetition rate of these two-way repeaters is set by basically this two-way signaling time. That you need to send a signal and wait for a heralding signal to come back. I should though stress, of course, that having more than a single memory, you can still improve on this time by basically multiplexing. For these repeater spacings, for two-way repeaters, you often find when you look at the literature and how people optimize things, that the optimal found around 30 to 50 kilometers. So it's like an order of magnitude higher than for one-way repeaters. But in this talk, as in the previous, what I will focus on is one-way repeater. And in particular, because we don't need this quantum memory. We don't need this long-lived quantum memory. We only need enough memory to process our error correcting code, basically. And then that allows us to dive into some systems that maybe do not have long spin coherence, but very good photon emission probabilities, emission properties, because that is what we need in order to create these error correcting codes. So not taking into account the previous talk, then a large part of previous work on one-way repeaters has focused on two types of encodings. One is the parity encoding, where you encode into concatenated EZ states, basically. And there's been some studies where one envisioned to have matter qubits to emit the photons and to do 2-qubit operations between photons. And for such proposals, it's estimated that you need, around hundreds, 200s of matter qubits per repeater station, and actually in order to run this repeater. In the same way, you also need kind of spin photon gates. You need the same number of operations. And this is basically because these numbers directly scale with the size of the encoding. There's also been considered some tree cluster encodings, which was actually first envisioned for photonic quantum computation, and in particular in all optical repeaters, where they consider that you don't use these spin qubits, but you have some single photon sources. You combine them with beam splitters in order to create these states here. There's been some resource estimations that you need more than 1 million photon sources per station, and you basically need to make very large encodings in order to have these repeaters work. So the motivation for our work, which I guess was also, is basically to reduce these resources. So can we make a repeater, and one repeater that does not require these kind of daunting numbers of resources? And we actually thought that these matter-based things are promising because they can actually emit quite a few photons, just a single spin. So we came up with a proposal, call it a tree cluster repeater. And here you see a high-level sketch of it. So let me just quickly go through what happens on the high level. So these boxes are repeater stations, and what you see in between are basically some encoded photonic tree. And we're focusing on this tree cluster encoding. So for tree cluster encodings, if you use them for one-way communication and not as for like memories, basically, then you can imagine that you have a single root qubit that is connected to a tree of photons. So these circles you should think of as photons, and then you have a cluster state, a tree cluster state of those photons. If you want to encode a qubit into that, so now imagine this qubit is another spin, but it could also be that you just do an operation here if you just kind of have a classical description of the qubit. Then you do a Bell measurement between your qubit that you want to encode and the root qubit of this tree, and then you're done with it, basically. After that, you send your tree down the repeater line. When it arrives at the next repeater station, it will have lost some photons, basically in transmission, in outcoupling, and all these kind of imperfections. You will have lost them, and now you need to retrieve your qubit information and re-encode it into a fresh tree. And the nice thing about the tree cluster is that for this re-encoding, all you need is actually to do one Bell measurement between one surviving first level photon. So if I think of the green ones as the first level, and the blue as the second, and the purple as the third, then just you need one surviving first level qubit and do a Bell measurement with the spin, the root qubit of the another tree. And then you need to measure all the remaining photons out with single qubit measurements. And that way you do the re-encoding and you correct for the loss. So you don't need this number of spin photon gates that scales with the size of the encoding. You really only just need one successful one. So this you continue down the line, and then when you end at your target station, you want to do your QKD. So you measure one of the first level qubits again in your QKD measurement basis, so one you've picked randomly, and the rest you measure out with single qubit C and X measurements. So that's basically how it works. One-way repeater on tree cluster states. I can try to give a very quick kind of a little bit of intuition. Why does the tree cluster encoding work? So if we think about a rudimentary tree here, so I call it a two-tree tree because it branches in two, and on the next level it branches in two. Then it will have this kind of notation in if you view it as a ket notation. After we encode a qubit with, say this qubit has alpha 0 plus beta 1, we'll have this state. And we can now look at what happens if we lose two photons. So if we lose this photon and we lose this photon, we'll have this state here, or we will have the bottom one. And what is important to note here is that by measuring on the surviving qubit here, we can actually recover which of these that we are in and recover the qubit information. And what you think about is that if we have this qubit, then to detach this tree, from that tree, we'd basically do a C measurement of this one. But if it's not there, we can actually infer what the C measurement would have been by measuring in the X basis on one of the qubits connected to it. Of course, this tree is not really loss tolerant, but by increasing the encoding size, you can make them loss tolerant. Okay, but what we really care about are resources. So how do we actually create these states? So here we make use of a quite old proposal now, actually, from Lindner and Rudolph. And I think they refer to it as the photonic cluster machine gun. The idea being that if you have a quantum emitter, you have two stable ground states, 0 and 1, and one is coupled to some excited state by an optical transition. Then you can first create your spin in the superposition. You put a pulse to excite it, and then it will decay and emit a photon. Then you can flip your states, 0 and 1. You can then do another excitation pulse and emit another photon. So what this amounts to is that if you were in the state that we'll have created after this will be the spin in the 0 state and a photon in an early time bin, or being in the 1 state and a photon in the late time bin. So basically you have a photon qubit now in time bin encoding entangled with your spin. And you can then continue to doing that by just repumping it. This is where the machine gun comes from. And you create basically a GZ state. If I put Hadamard's on the spin in between the repetition, I will create a 1D cluster state. And it was realized by Borregaard and co-workers that this you can use actually to create these kind of tree cluster states with emitters quite efficiently. So if you imagine that we have a memory spin, it's a root qubit, and we have a quantum emitter here, we use the Lindner scheme to basically make GZ-like qubits. And we can also swap the state. We can do a Hadamard and then swap the state to this photon. Then we can detach the spin, the emitter, by measurement or by clever emission scheme. And then we can reattach it to the node and then do it again to create another branch of the tree. And this way you can kind of repeatedly emit or sequentially emit the branches of the tree. And if you have a tree cluster where you have a certain depth, so how many times it branches out, and a certain branching ratio, then basically the number of spin qubits that you need is more or less the depth of the tree.
Oh, sorry, can I interrupt you? There's a question.
Yes,
so,
please.
Perhaps Martin Kubich can ask the question. Otherwise, I read it. So the question is, if you do, he has trouble with audio. So the question is, if you do tree clustering and the subsequent transmission of multiple photons, do you preserve the security feature?
Yes, because the tree cluster really only contains the information of one qubit. And unless you lose, I mean, as long as you can reconstruct the qubit information with the photons that you receive, that ensures that basically no one else can reconstruct it somewhere else with the photons that was lost.
Okay, thank you. So,
all right, great. Thanks for that question. So coming back to this, I think the important part here is that the number of spin qubits you need scales with the depth. And what we actually found out is that for a reliable transmission over, for example, 1,000 kilometers or even longer, you only need depth 3 trees, which means, that to generate your state, you basically need 1 emitter and 2 memory spins. So that's the resources we need so far. We'll keep that in mind. Then the other operation we need to do is that we actually need to do this re-encoding at the repeater stations. In order to do that, we need to make a loss-tolerant Bell measurement. What I mean by loss-tolerant is that if we just tried with without knowing which first of a few qubit actually arrived, and we tried to make a gate between that, our root qubit of a new tree, then if that photon turned out not to be there, we would need to generate the entire new tree, because otherwise we would have a buildup of error, basically, because we didn't know whether the photon interacted with the spin or not. So what we propose to do is basically that we first try to swap the information of one of the first of a qubit onto an auxiliary spin. So this is what depicted here. They have an auxiliary spin, basically an emitter, which is kind of the same thing we need to generate the state. And then I'm sure you're aware of these nice works where basically you can make a controlled phase gate between a photon and an emitter, where you exploit that one of the qubit states is optically coupled and the other one is not. And then if the photon impinges on this one-sided cavity and the qubit is, or the spin is in a 1 state, then it will be reflected without any phase. And if it's impinges on the cavity and the spin is in the zero state, it will be reflected with a pi phase. So this is basically how you enable this controlled phase gate. And we then simply just then take one level photon, try it, and then we should detect it afterwards, because we're basically making this circuit down here. Then we come in with our photonic state in some psi, we do a controlled phase gate with our spin, and then we measure out our photonic qubit in order to transfer the information to the auxiliary spin. And if we don't detect it, we know something was wrong. We just reinitialize our spin and try with another photon. In this way, we can try until we have a success. And once we have a success, we then do a deterministic Bell measurement between the two spins that can couple through near field coupling. And I should say that the fact that we have Herald here makes this gate quite robust against typical infidelities. So if you look at the cooperativity, which is basically the ratio of the good coupling between this emitter and the cavity, and bad coupling, such as spontaneous emission and cavity losses, then the error scales down with the cooperativity squared, which means that a cooperativity of 100 will already give you an error of 10 to the minus 4. So with such kind of numbers here, this would be a fidelity of your operation, and you would have a success probability, which is very close to just being your detection probability of your photon here. So the resources we need here for this operation is basically one emitter and a memory spin, which is the root qubit of the new tree. And this emitter is exactly the same level strip that we need for the emitter from the generation, and we need a memory spin as in the generation. So if we add this together, we actually, the total resources we need for both the state generation and the reencoding is one emitter and two memory spins. All right, so let's see how this performs. So how do we calculate the rate of transmission? Well, we have some repetition rate of generating our state. That will depend on how many photons n is in the state, the time it takes to emit a photon, and the time it takes to make a gate between memory spins, or memory spins and emitters. And then we will have basically what is the overall transmission probability from sending a state from the start to the end. Well, we'll just take and say there's some probability in eta e to transmit from one station to the next, and then we'll take that to the power of the number of repeater stations, basically. But what saves us is that because we encoded, that transmission here can be very close to 1. Of course, it will depend on our specific encoding, and will depend on our bare transmission loss in the line, and our detection efficiency. And this also includes basically in-out coupling losses. This encoding is actually only correcting loss. It's not correcting faulty operations. So when we send this, every time we do an operation, basically this re-encoding, we're basically building up error. So if this error is small enough, we can basically say, well, if we have m stations, it's more or less m times the re-encoding error for each station. This re-encoding error, we model as basically how does that depend on if we just put a depolarizing channel on each individual qubit of the photonic state. That will result in a certain re-encoding error at the logical level when we do this Bell measurements. What we then got was a result like this. So this plot here shows a distance in kilometers, and we have the secret rate here. So we are imagining that we try to extract key with this. And what we have assumed is that it takes about a nanosecond to emit a photon, that a gate time takes 10 nanoseconds. And for that, and a re-encoding error of, a single qubit depolarizing error of 0.1 per mil, you would get a secret bit rate of about 0.1 megahertz over 1,000 kilometers. And your encoding would only consist of 265 photons. And basically, we modeled our bare transmission rate in this way, so note that our detection and in-out coupling is at 95%. If the gate time is a little slower, about 100 nanoseconds, then this would drop from 0.1 megahertz to about 10 kilohertz, I should say. Okay, and these 10 nanoseconds gate time, we imagine that's something we could envision, for example, with quantum dots. The bit slower gate times of 100 nanoseconds is something that's a bit more suitable for diamond vacancies, like silicon vacancies. But we're in the case, we're looking at rates that are about megahertz to kilohertz, tens of kilohertz. All right, and this brings me to the end of my talk. So I hope I've convinced you that this was a proposal for a one-way repeater based on photonic tree clusters. And for distances up to 1,000 kilometers, you basically need 3 spin qubits per repeater node. And that would enable you, with the parameters that I specified, to get key rates on the 100 to 10 kilohertz or 0.1 megahertz. And we also discuss in this application here a bit more outline how can you implement this with diamond defect centers or quantum dots. I think the main challenges is basically the inefficient in-out coupling, but I think actually relating to the comment that was on the previous talk, it's actually been demonstrated that fiber cavity coupling above 90% now. So it's still improving and getting up there. And I think the 85% is actually including both in-out coupling and detection efficiency from the Lucan group. But we also need something that we have swept on the rug now, is that all these systems, they do not emit in telecom, they emit in optical. So we need telecom conversion, and that also needs to be at this efficiency level. Then another thing is that the gate errors of the 0.1% is needed for high rate and long distance, which is very challenging. I should though note that this is the same more or less for all of these one-rate repeaters that has been described previously. So in that sense, it's a little strange that ours, which actually do not correct errors, kind of need the same thing for 1,000 kilometers. But with that, I'll conclude my talk, and I would be happy to answer any questions.
Okay, yes, thank you very much. Perhaps you can ask first, then people have time to think about questions. Our standard question: what do you think will be the first use case for entanglement-assisted communication networks?
Yes, so I thought about that question, and I was maybe, it depends a little bit what you mean by entanglement-assisted communication networks. I would say for me, when I think about that, I really need entanglement over a distance. And then I would say, then I also need that to transmit a qubit, for example, over a distance. So I think my vague answer here will be that I think the first application of quantum communication will probably be QKD without entanglement. And the next thing might be improved QKD using entanglement.
Mm-hmm. Okay. And you have it already some parts, and the main challenges are perhaps the same as on your slides, or is there other main challenges? The second question is on the path to realizing this use case. What is the current main challenge in your field?
Yeah, I think in order for this use case to be useful for anyone outside of just pure scientific interest, is really the rate question, right? So if you want to have secure bits transmitted, you need it at a pretty high rate in order to do any meaningful communication. And all current experiments, the rate is just not adding up. It's just not fast enough. And I mean, to add words to that, we also talk about this telecom conversion. For many of the promising technologies, you need telecom conversion, which also needs to be efficient in order to get to high rate. So I think telecom conversion is definitely one of them. Efficient in-out coupling, I think that's really improving, but for kind of single systems here and there, if you want a viable technology, of course, should be kind of something that's broadly applicable. But I think that the rate question is really the main challenge.